Hi, everybody. We are back, and in this brief segment, we're just going to talk about three different metrics that can be used in order to think about measuring the performance of your regression output algorithm. So these metrics are all typically can be used almost interchangeably in a situation where we are making a prediction, and our prediction is being mapped into some continuous output space. So the first metric we're going to talk about is one that actually you may be fairly familiar with. This metric is called the sum of squared errors, also referred to as the sum of squared residuals, specifically in the context of our linear regression model. And this is one of many metrics that can be used for evaluating predictions. And these metrics are going to be useful, as we're going to see momentarily when we start getting into this issue of training versus testing, that we want to measure both in-sample error and out-of-sample error for our predictive models. And it's good to have some sort of benchmark metric to use to compare the two. And one of these metrics, the sum of squared errors or the sum of squared residuals, recall was the objective function that we were dealing with when we were solving that cost minimization problem in the context of a linear regression problem to find those pseudo-inverse estimators for the betas, for those beta coefficients. So the way we calculate this should be fairly familiar here. We're going to look at the distance the actual observation yi is from the value that is predicted by our model, which is y hat. And then we square that distance so that the positive and negative residuals do not cancel out when we sum them up. And this measure, again, is the total squared deviation in the actual data relative to the prediction. Okay. It is the expected or predicted value conditional on the inputs, right? We're measuring the expected or predicted value, y hat, relative to the actual value y. And again, y hat is calculated conditional on those x variables on the right-hand side of our regression. Another metric very closely related to the sum of square errors is something known as the mean squared error, or MSE. And this is easily calculated by just transforming the sum of squared errors. So the mean squared error sounds like what it is. It's taking the average of the sum of squared errors here. So you can think of this as like the same cost function that we had dealt with in the linear regression framework, but now we've divided the objective function by n, or equivalently, we've multiplied the objective function by 1 over n. And what does that do to a function if you multiply it by a constant or divide it by a constant? Well, it stretches it up and down, but it will not change the property of the optimum. Okay, so if we had used the SSE measure as our cost function, or we had used the MSE measure as our cost function, okay, we would get the same parameter values for beta at the end of the day here. So this measurement, a little bit different interpretation. It is measuring the average squared deviation in the actual data relative to the predictions. Okay, we're looking at the expected value conditional on the inputs. That again is what y hat is. And this measure will have units of measurement of the output variable squared. Okay, and that is an important element here because that is very similar to another metric that you have seen before in statistics. And that is the variance of a variable. Okay, if you look at this, this is almost exactly how we would calculate the population variance for y, except instead of y bar here, we have y hat, right? What was y bar? Well, y bar was the unconditional expectation, right? Y hat, though, is the conditional predicted value of y given our inputs. So again, the analogy here is that the mean square error is almost like we're computing the variance, but instead of measuring the deviation in y relative to its unconditional mean, we're measuring it relative to its conditional mean, which is the expected or predicted value conditional on the value of the independent variables in the right-hand side of our model here. Note that we actually, it's pretty standard not to make a small sample adjustment, so I want to be clear about this. It's a little bit different than the squared residual standard error, which would make a degrees of freedom adjustment in the denominator, which we saw the sample variance had done, right? We divide by m-1 instead of n, but we don't actually typically make that adjustment here since we're just finding some arbitrary benchmark related to that sum of squared errors. One of the most popular metrics to use in evaluating the efficacy of a predictive model is something known as the root mean squared error, or RMSE. And you generate that by just taking the square root of the mean squared error. So there's the square root of SSE over n, okay, which means we're taking essentially the square root of our sum of squared residuals divided by n, which is the average squared residual there. And then we square root that. So now the units of measurement are measured in the same units as the original output variable y. Okay, note that, again, this looks kind of familiar. This looks a lot like how we would calculate the population standard deviation, right? Just the square root of that population variance. But again, instead of measuring those deviations relative to y bar here, we would be measuring them relative to y hat, which is our predicted value. Again, the conditional mean of our prediction, conditioning on the right-hand side variables here. And again, for this one, it's pretty standard to not make a small sample adjustment for degrees of freedom. So that was just a real quick rundown of these different error measures. You should be able to go back and take a look at some of the questions that we had done where we had done things like simulated out of sample prediction error, and I'm pretty sure you will see some of these metrics in those types of problems. Hope you enjoyed. Stay tuned for more. We will start getting into the idea of training versus testing and negotiating the bias variance trade-off and thinking about model complexity. So we'll see you soon.